Today, I want to talk about Dijkstra's shortest path algorithm. Edsger Dijkstra was a Dutch computer scientist. He received the Turing Award in 1972 for his advocacy on structured programming. This programming paradigm uses structured controlled flow as opposed to unstructured jumps, such as using goto statements. Among his many contributions, one of them is the shortest path algorithm, which we're going to talk about today. This algorithm was conceived in 1956 and was published in 1959. First, I will run through a simple graph using the algorithm, and then I will discuss the pseudocode. Let's start with this graph. Suppose we want to find the shortest distance from A to F. Or alternatively, we can say, let's find the shortest distance from A to every other node on the graph. In both scenarios, the approach will be very similar or the same. First, we had to set up several data structures for this algorithm. We would need an array or hash map to store the minimum distance from every node on the graph to the source node. The source node here is A. In addition, we would need a mean heap where we're going to store a list of tuples. Inside the tuple, we would have the node of the graph and also the weight. The weight here is the combined distance between that node to the source node. In this case, it's the combined distance from that node to A. For example, in this path, going from A to B to D, the combined weight or the cumulative weight for D is 3. In addition to these two data structures, we will also have a variable called current. Now let's go through the algorithm. The first step, we put the source node and a distance of 0 on the heap. And then we're going to go through step 1 to 4 repeatedly until we are done finding the minimum distance between every node and A. So let's go through this. Step 1, we take the nodes with the minimum weight from the heap. So far, there's only one item on the heap. So we take A. A will be the current. And then we update the minimum distance of this current node. So A, the distance between A to A is 0. And then we're going to get all the neighbors of current, so all the neighbors of A and their distance. The neighbors of A are B and C. We're going to put B, 1 and C, 2 because we want to get the distance as well on the heap as a tuple. And now we repeat steps 1 to 4 again. We take the top item of the heap. Now this is a mean heap. The tuples are sorted by the parameter weight. The item with the smallest weight will be on the top of the heap. The top of the heap is B, which has a distance of 1. So we take B as the current, and then we update the table for B here as 1. The weight value in the current tuple is the value that we want to use to update the minimum distance table for that current node. Once updated, that value is the minimum distance from the source node to that current node. For example, in this step, we now have established the shortest distance between A and B as 1 unit. Now we get all the neighbors of B. The neighbors of B are A, C, and D. For A, we have already established the minimum distance, so we will ignore that node. We are now making a tuple for the node C and D. For C, we have to make a tuple with C and the weight. The weight here, as mentioned before, is the distance between the source node, in this case is A, so it's from distance from A to C. The distance between A to C can be decomposed into the distance between A and B to C. Now we know from looking at the graph, B to C has a weight of 2. So what's the distance between A to B? We can get this value when we look up the table here, the minimum distance table. This value is 1. In fact, we can get this value from 2 locations because we just used the value here in the current tuple to update the minimum distance table. So the value here is same as in here. Since A to B is 1, B to C is 2, then we know that A to C is 3. We will make the tuple C3 and put that on the heap. The next neighbor is D. Again, we are making a tuple with D and the weight is the distance between A to D. We will decompose the distance of A to D to A to B and B to D. Looking at the graph, B to D has a distance of 2. A to B, we can obtain this value by either looking at the minimum distance table here or the weight of the current tuple here. Adding these two values together, we have the value of 3. So the tuple D3 goes onto the heap. Just to summarize this part, when we make a tuple for the neighbor, the weight inside the tuple comprises the distance between the current node to the neighbor's node, which we're going to consult the graph, and also the minimum distance of the current node to the source node. For this distance, we can either consult the minimum distance table or the value in the current tuple here. In all the future iterations, I would just use this value in the current tuple. Now we repeat the process. The top of the heap is C2, and C2 comes out. And then we will update the minimum distance table with the weight in the current tuple. So the minimum distance from A to C is 2. C can go to A, B, D, and E. We have already established minimum distance to both A and B nodes, so these two nodes will be ignored. We will only look at D and E. CD has a distance of 3. Remember, we have to add the value of 3 to the values here at the current. So it's 3 plus 2, we got 5. This goes onto the heap. C to E has a value of 4, and 4 we have to add the value of the current distance here, so that becomes 6. So E6 goes onto the heap. We repeat the process again. The top of the heap is C3, and C3 we don't care because C is updated already. We already found the distance between A to C as a distance of 2. So this is discarded. And the next item is D, so D3 comes out as the current. We do an update of the minimum distance to D, which is 3. D can go to B, C, E, and F. B and C are nodes that we have established this minimum distance, so we don't care about those two nodes. D to E has a value of 4. Again, the value of 4 will add to the distance here at the current as 3. 4 plus 3 is 7, so E7 goes onto the heap. D to F has a value of 4. Again, we'll add the current distance here, becomes 7. So the tuple is F7, and that goes onto the heap. In the next iteration, we look at D5 is the top of the heap. D is already updated, so we don't care. And the next item is E6. E6 becomes the current. We do an update of the minimum distance table for E as 6. E can go to C, D, and F. C, D are both established, so we look at F. E to F has a distance to 1. And then we take the 1 here, and then we add the 6 here, and we get 7. So F7 goes onto the heap. Now the top of the heap is E7, and E we already established as having a minimum distance of 6. So we take that out, and the next item is F7. So F7 becomes the current. We update the values 7 here on the table, and then all the neighbors of F, which are D and E, has been updated, so we don't put that on the heap. And then there's only F7 on the heap, and F we already established, so we are done. It is worth noting that every time we take the top item off the heap, we always check whether that node, the current node, whether the distance has been updated in the minimum distance table. If we see that the minimum distance is updated, then we will skip that node. If it is not, then we will update the table. When we select a node from the heap and we get the distance, that distance is the shortest distance between that node and the source node. Put it another way, for each node in the graph, when we establish the minimum distance and we update the minimum distance table, for each node, that update was done once and only once. To illustrate this point, you can see on the right, here is a simulation of how Dijkstra's algorithm works. When it's searching, the edge is blue. Once the minimum distance of a particular node is established, the line becomes red. Now you can see that once the line becomes red, that line does not change color. Once the shortest distance for a particular node is established, it's never the case that down the road, the algorithm will find another path with a shorter distance to that node from the source node. I will stop here for a bit to let you look at the simulation. Before we talk about the pseudocode for Dijkstra's algorithm, let's talk about the data structures that we would need. We will need an array or a hash map to store the minimum distance from all the nodes on the graph to the source node. In this data structure, usually I will initiate all the values to be -1. This way, it's easy to check which nodes we have established the minimum distance already from the source. Another data structure we will need is a mean heap. This stores a list of tuples, which comprise the node and the accumulated distance from that node to the source node. The mean heap will sort these tuples based on the distance value, and the top of the heap will have the tuple with the minimum distance. As we are searching in a graph, we will have to assume that either we are given the graph in the form of a adjacency matrix or adjacency list, or we have to build up such representation of the graph. This is the pseudocode. First, we push the source node and the distance of 0 onto the heap. First item is the source, so that always has a distance of 0. And then we're going to put that 1 to 4 inside a while loop. So while the heap is not empty, we will take the item with the lowest distance of the heap. And then we check the minimum distance table. If the minimum distance for that node is established, that is, the value is not equal to -1, then we'll skip it. Otherwise, we will update the minimum distance table with that distance. In the next step, we're going to get all the neighbors of that node by consulting the adjacency list. For each neighbor, if the minimum distance of that neighbor has not been established, then we'll make a tuple with that neighbor node. The tuple comprises the neighbor node and the accumulated distance between the neighbor node and the source node. To compute the accumulated distance, all we have to take is this value here, which is the distance between the node and neighbor, and then we add this value, which is the value for the distance between this node to the source. So just to emphasize this a little bit, the tuple inside the heap comprise the node and also the accumulated distance between that node and the source node. The tuples in the adjacency list comprise of the nodes and also the distance between the neighbor's node to the key node. When we add these two distances, we get the accumulated distance between that neighbor's node to the source node. And that is the algorithm. It's not very difficult. It's like a breadth-first search, but unlike breadth-first search, it does not have a hash set where we keep track of which node has been visited or not, and we don't need it. In Dijkstra's algorithm, the minimum distance table serves a similar purpose. Each time we process a node or we decide whether to put a node on a heap, we always check for that node whether the minimum distance has been established, and if that is the case, then we will skip those nodes. Let's talk about the runtime complexity of Dijkstra's algorithm. If we are looking for the minimum distance to a node or all the nodes, potentially we have to run through all the edges of the graph. All these edges of the graph potentially will be in the mean heap. To find the lowest item in all these edges, that is a log E operation where E is the number of edges in the graph. So the runtime here is big O of E log E. Now, potentially you can bound this a little bit tighter, but I think no one will fault you if you say it's a big O of E log E. Dijkstra's algorithm is very similar to Prim's algorithm. I had discussed Prim's algorithm in earlier videos. I left a link to those videos in the description below. Prim's algorithm, when we're building the minimum spanning tree, we always take the node that's closest to any nodes from the existing spanning tree that we're building. While Dijkstra will take the closest node from the source node. So that's the distinction there. And the important aspect of Dijkstra's algorithm is that it can only work on graphs where all the edge weights are positive. If there's some edge weights that are negative, the algorithm may provide an incorrect answer. Now, one may ask, if we have a negative weight, what if we add a constant to all the edge such that all the edge will be positive? Would that work? And the short answer is no. Here's an example. On the left-hand side, we have a graph, and one of the edge is -9. Suppose we add 9 to all the edges, we get the graph on the right. The shortest distance between A to D on the left-hand side is this path. While on the right-hand side, the shortest distance between A to D is this path. Here you can see that adding a constant to make all the edges positive and then running Dijkstra would not work for this graph. In the following several videos, we would use the templates that I showed earlier, and we're going to run Dijkstra's algorithm on a series of LeetCode problems. I will finish today with several quotes from Dijkstra. Hope you enjoyed them and hope to see you next time.